Hello, hello. I was just reading Tom's comment about it. Better be a good show or else I want my money back. Well, hello, hello, live in 1080p. So you already got your money's worth because we're doing a test upgrade of our StreamYard account and seeing if 1080p is worth paying for. Well, worth paying like twice as much for, essentially. So yeah, exciting new stuff. So yes, today it is just me, and I thought it would be a good opportunity to talk about what I've been doing in my Making Embedded Systems class. So for those of you who don't already know about the class, it is a class taught by Elecia White, whose company is called Logical Elegance. Say that 5 times fast. Logical Elegance. And Elecia and her partner, Chris White, they do a podcast also called Embedded.fm, and it is an excellent, excellent podcast where she interviews a ton of different people working in the space, you know, from people doing like kind of hardcore industry things, as well as artists and everything in between. And it is a great, great podcast that it puts a spotlight on all of the nooks and crannies of the embedded world, from the software to the hardware and all sorts of different use cases and all sorts of different people. And it's really cool. And you should definitely listen to it. But anyway, Elecia is teaching a class on Classpert, and it's called Making Embedded Systems. And it's a 12-week, pretty intensive course on embedded programming. It does assume that you already know, that you're already pretty familiar with C. So it's if you don't know how to program in C at all, I would say like get familiar with that first before considering taking the class. I am mostly familiar with C, although you know, it's been a while since I had a class on it. But even if you're still already familiar with it, but maybe don't know all of the ins and outs, even if pointers take you like a little bit of like working and wrapping your head around to understand, it's still like a great class for all that. And there's been a lot of help from the other classmates and the mentors and everything in it. So that is all great. And in fact, there's a live homework session that happens right now every week that I always tend to miss. So I'm going to actually try to make it to the last half. So I think I'm going to cut this off at 6 tonight. But anyway, so I'm taking this class and we have to do a final project for it. And of course, the final project is making some sort of embedded system, and you have to use an ARM processor. You're not allowed to use the Arduino framework, and there are a few other things. You have to have at least 3 different peripherals or different types of things that you're interacting with, and you have to have an interrupt from a button, and you have to do something with the serial data output. So kind of covers everything. I'm, of course, trying to make this class do double, triple duty because I have like no free time at the moment. And oh, hello, Bob, and hello, David, and hello, Tom. Late on my hellos. So I'm making this class do like double, triple duty, and I'm thinking like, okay, well, maybe I could make something for the final project that would also be a cool kit that we could then like sell in the shop. And so that puts a few more constraints on what my final project is, because I feel like it has to be something that I think is useful to other people. And key point this year, it has to be with a processor that I can actually buy. That's the hardest part. And but I was like, hey, guess what I can buy? Guess what everybody can buy? Everybody can buy RP 2040s, which is the Raspberry Pi 2040, which is their new small ARM chip. And I can use a Raspberry Pi Pico as a dev board, and we can go from there. So that's what I've been doing, and I've been learning all about the Raspberry Pi, the RP 2040 and the Pico, and the software development kit that Raspberry Pi has written for it. And I'm also using VSCode and Platformio, which are new pieces of software and new environments for me. So yeah, it's been a ton of learning, a ton of new things. So I thought I would talk about the final project that I'm coming up with. And like show you Platformio and VS Code and the platform that I'm using, and like maybe a little bit of the Raspberry Pi SDK. And I, of course, have some hardware to show you too. This is my test setup here. And I'll talk about that more in a little bit, but I just wanted to give you a little bit of a peek at the hardware, because that's the fun part. So first of all, I think I will go over what the final project is. I think that seems to be a good place to start. And if anybody has any questions during it, definitely chime in. Feel free to let me know. I might not know the answer, but I might, and we can figure it out. All right, so let's see. We are now going to share this screen. So this is my GitHub repo. So you too can check out my final project as it goes along and all of my homework for class. So it's under like my personal account name, which is CA Sundra, and it's called Making Embedded Systems class. And I believe that week 4, yes, week 4 is the goods, I think. Yes. Okay. So my idea is the PALED. So the PALED is going to be an LED PAL, so which is also a palette, kind of like an LED, like painter's palette. So yes, a little play on words, a little punny there, couldn't help it. And the idea is I want people to be able to look at the colors of addressable LEDs and be able to come up with color palettes based upon like what the actual LED colors look like, instead of like trying to design a color palette on the computer and then you get approximately what those colors are on your LEDs, and then like you're maybe going back and forth. So this is for people who are maybe trying to match LED colors with certain types of branding, or they have like particular color schemes in mind. And they want to translate those colors to LEDs and see how they look on the actual LEDs. I think that I might also have like a few different diffusion options as well. So just, pieces of plastic that you can put over the LEDs that will, make them more diffuse. Maybe some of that black LED acrylic as well, like have a white diffuser or black diffuser or that kind of thing. And so let's get into it though. So the general idea, this is my crappy sketch because everything starts out as a crappy sketch. So my first idea, and it looks a little bit different now, is that it'll basically be a box. Oh, and by the way, I should say, I was totally inspired by Deborah Geek Mom Projects on this, because she showed me a box that she had that had 3 knobs on it and a little LCD screen, and I think it was like just an LED ring. And basically you could dial in, the knobs were like red, green, and blue. You can dial in each color. The LCD would tell you like what the RGB values were, and I think maybe even the hex code for that color. And the entire LED ring would just be the color that you dialed in with the knobs. And so that was sort of like my original thing. I was like, oh, that would be a really cool kit. And I know that Jason Kuhn has made something like this too, and he has some instructions on how to make that online somewhere. We will try to dig up that link and put it in the description at the end in a couple of days. But yeah, both of them have made these kind of projects, and I was like, oh, that would be like a really cool kit to have so that you could grab a bunch of parts. But then I started thinking about it, and I was like, oh, I think I could like make this even cooler and more useful and kind of like kick it up a notch. And that's where this whole idea about color theory comes in. So, okay, just to close out the hardware part of this. So the middle here is the LCD, and so it would show you, red, green, and blue values, maybe like the 8-bit values for each color, and maybe also the percentage, like if you were doing a PWM, like what the duty cycle would be or something like that. And then you have some buttons here, RGB under here are your knobs. And then, you have an LED strip here. That strip is now going to be a matrix. And also there's going to be an LED ring associated with this as well. And then there's like a USB port for some extra data. There might be analog RGB LEDs as well that are driven by PWM. It kind of depends upon how many spare IO I have at the end of this. I thought it would be really cool to compare analog LEDs like at the same PWM settings essentially as the RGB LED, like the addressable RGB LEDs would be, and see the difference between the addressables and like the analog ones. But yeah, in order to do that, each analog LED needs 3 PWMs. And the Raspberry Pi Pico is like crazy flexible. And it has a whole bunch of PWMs on it, which is super cool. But it still only has like 30 or 32 signals. And a lot of them are eaten up by other things. So maybe I'll have that, maybe not. We'll see. Okay, so that's the hardware. The color theory part of this is that dueling RP2040s on the thing. Yeah, I'll get into why there are 2 in the test fixture in a bit. It's actually because one is the debugger for the other one, which is kind of cool. Cheapest debugger ever, $4, right? Am I going to make the 2 boards fight? Absolutely, they will fight. They already have, actually, and fortunately it was a draw. I'll get into that later too. Okay, so color wheel theory, like what's happening here? So the idea is that the LED ring will be your color wheel, and it will be fixed like this color wheel that you're seeing on the screen right now. Red will be at the top, but these will be all discrete LEDs, probably like I have a 16 ring right now, this one that I'm playing with. So at least 16, maybe even bigger, we'll see. So discrete LEDs, and that will represent these different color spaces around the color wheel. It'll be fixed with like red at the top and green at the bottom like that. So your button takes you between different modes. First mode is going to sort of be the easiest. It's going to be monochrome mode. So in monochrome mode, you basically have one color, and you'll be able to dial that in with the knobs, or you could probably like also tell it what color to be via the serial port, so via USB and a COM terminal on your computer side. And so you'll see on the matrix, like this part basically represents what you'll see on the LED matrix. I'm not sure exactly the size of that right now. I would say at least 4x4, maybe more. Figure that out in a bit. I think I have like an 8x8 one right now to play with. So this will be your matrix, and this is your main color here with the big color bar. And then below it, it'll basically show you that same color, but with a variety of brightnesses. Of course, dark is hard to do with LEDs. Dark is just, the absence of color, the LED getting dimmer, essentially. And then, of course, like more brighter towards this section. So this will basically be this main color, but at different brightnesses. So that helps you design a monochromatic color scheme. The LCD will display the RGB information for this main color, and it'll also display like kind of how to get to these colors. So, this will be sort of the center. It'll tell you where the 2 endpoints are, how far away the 2 endpoints are, and where they are in the middle. And so the LCD has to be somewhat compact in the information that it's giving you. So it'll basically tell you how to get to the other colors from the main color. But the serial port will eventually have the ability to output all of the individual color information. So it'll be able to output RGB values for each one of these. And then, so in this mode, your knobs start to do different things. So when you adjust your knobs, one knob will just adjust where the color is around the color wheel, so you'll be able to change your main color. And then the other knobs will adjust kind of the range of brightnesses. So like maybe this one is kind of too dark for you and you don't even want to see it, but you want to see more points in between this light one and like this medium. So one knob will basically just expand or contract that range of brightnesses. And then the other knob will sort of like let you move where that range is from all the way light to all the way dark. So one will like move where the range is, and one of it will tell you like how big or small the range is. Yeah, so cool. Okay, so that's monochrome. So then you have complementary. The complementary color is the color that is directly opposite the color wheel from your main color, from your like chosen color. And you know, complementary color schemes tend to be very contrasty, have like a big effect. So sometimes you have like your main color and then you use contrast color for like these little accents here and there. And now so the knobs would basically do the same thing in this mode, because that complementary color is fixed. Like the complementary color is exactly 180 degrees across the color wheel. So if you change the main color, both of those will sort of rotate around the color wheel, right? But really your knobs still do this thing where they adjust the monochrome range beneath it, because it's always nice to have like, you know, some shades of your main color and some shades of your complementary color when you're like putting together color schemes. Now it gets interesting. Split complementary, now we have 3 colors. So you have your main color, and then you have 2 colors that are just to either side of the actual complementary. And this has like kind of more interesting color schemes where you start to like sort of see that these colors are contrasting, but they also kind of go together. They're kind of pleasing to the eye. And now what the knobs will do is one of them will actually vary the angle between your main color and your 2 split complementaries. So your main color is here. If you move your main color, all of them rotate as a group, right? But then if you move the angle of the split complementaries, those will either get closer together and more towards the actual complementary color, or they'll get further apart from each other. Now, when they like get perfectly apart from each other, that's called a triad. And that's like a very 3 colors at like completely balanced spots around the wheel, right? It gets you something like this. And so, you know, this is still the LED matrix display. But then like sort of interesting things happen. Then when you start getting closer and closer to your chosen color, you actually switch at some point to an adjacent color scheme. So this color scheme has like 3 colors that are very, very related. Oh, and by the way, I got these like images from like kind of 2 different parts of a thing talking about it. I did credit where I grabbed them from at the top, Colorpedia. So just so you know, if you're wondering like, wait, where is the red and green below here? The colors that are represented in the matrix are not actually indicative of the colors that are chosen in the wheel. They're just like for visual reference. And yeah, so you can get to this adjacent color scheme, and then you get like 3 very related colors that are very pleasing together and not very contrasty. So another color scheme is this split complementary with complement. It's exactly what the previous color scheme was, but it just adds the exact complement into it. So then you sort of like get these kind of like fun and interesting color schemes. Again, you can vary the angles of those split complements, but now, because there are 4 colors, when they're all evenly around the color wheel, they are called a tetrad. And then you get like sort of this very sort of, I would call it like this primary-ish blocky color scheme where each color is like very distinct from the other one. But if they're all sort of in the same, like for LEDs, it would sort of be brightness range, they will still all look pretty good together. And then when you vary that angle closer to your main color, then you get an adjacent with complementary color scheme. So then you get these 3 related colors and one that's sort of your high contrast complement. And then the last official like color wheel scheme is the dual complementary. So it's just 2 pairs of complementary colors that you could change the angle between around the color wheel. And that one's kind of interesting. You just get, 2 related colors, but the related colors are not necessarily super related to each other. I also thought it would be interesting to add a gradient color scheme. It's not exactly a color wheel color scheme, but it basically, you choose 2 colors. So like, let's say I chose purple and green, and then you take the shortest path around the color wheel and fade one color into the other. So in that case, purple and green would sort of fade through blue. As you can see down here, purple and yellow faded sort of through magenta and red and orange. And I think that that's very useful too for coming up with like a nice gradient color scheme. So anyway, that's the idea. So you would be able to switch the mode with a button and switch between all these things, play with these color schemes, move them around the color wheel, and get RGB values and how to implement them in your own code from all of that. So yes, that is the palette, the LED palette idea. And yeah, I don't know. I think it would be kind of cool. It's a little specific, but that's okay. I'm also thinking back to sort of that original idea. Like I think, the full palette thing, you need encoders for knobs. That was like the first thing that I realized. So if I'm changing between these color schemes, right, I need knobs that don't really know or care what their absolute position is. So because basically when you switch between modes, the knobs will actually adjust different things. And because the knobs have a different function when you switch modes, if I was just using rotary potentiometers that have like a fixed 270-degree travel, if a potentiometer is set to one point and then the mode is switched, it will be set at a different setting now for this new mode, and that would cause all of your colors to change. And I thought that would be a very disorienting user experience. Like you would want your main color to stay consistent between the modes, and so you would basically kind of want your knob from the previous mode to sort of forget where it was and then be new on the next mode. So really, in order to do that, that means like you have to have continuous travel on your knob, first of all, and which rotary potentiometers are generally, not always, but they are generally fixed between like 0 and 270 or something like that. And then you also want, like, you want to know when the knob is moving, but you don't necessarily care about its absolute position. So that all points to encoders. Encoders are, here, let me make that big. Ooh, I need to, sorry, I'm not usually screen sharing, so I'm a little bit slow on it. Go back to this one. So yeah, so these knobs are actually encoders. It's going to be hard to show you without my fingers getting in the way. They don't have knobs on top of them right now. I guess I could have done that, but basically they turn all the way around, and they don't care where they are. There are 2 signal outputs that are both square waves, because basically this knob, inside of this knob are 2 little switches, and so every time you turn it, and you can feel there are sort of like these detents. There are these notches that it slides into. An example of this kind of encoder knob in practice is my car stereo. It's sort of like you can feel it ratcheting around, but you can like spin it all the way around as many times as you want, and it doesn't really care. That type of knob is an encoder. So every time it goes into like one of those little detent points, like it ratchets once, one of the 2 output signals for this knob, one of the 2 switches closes or maybe opens, And you get this pulse of square waves, basically, when you turn this knob. And so there are two outputs, and they're slightly offset from each other. So by understanding understanding that offset, you can actually tell if the knob is rotating clockwise or rotating counterclockwise. So it's all very cool, but it means that you definitely have to hook these up to interrupts because you have to catch that transition, right? If you just have software that checks the state of that knob every now and then, you might miss when that transition happens. And so you'll kind of lose sight of what that encoder is doing and which way it's rotating. Because it might have gone backwards, it might have gone forwards. You don't really know unless you can compare those, like when those transition happens, what the other signal is doing. And so like you definitely need 6 interrupts for 3 knobs, right? And that starts to like take up some processor pins and some peripherals. So yeah, Bob says, so for lack of IO pins, I2C port expanders to the rescue. I actually found a very specific IC that allows you to drive 4 analog RGB LEDs. So it generates 12, it can generate 12 unique PWMs from an I2C bus. And I did order a couple of those chips. They're a QFN package, so they would be a little bit challenging to solder by hand, but probably could do it. But it's always, it's one of those things that it's like, there is one chip that I found that did this very specific thing, and I always hesitate to design something so unique and special into a product, because if it goes away, then you're kind of hosed, and there might be more generic ones. I didn't do a ton of looking. There might be like a little more generic I2C to just PWM that didn't necessarily also incorporate like the current driving characteristics that the specific LED driver did. But I was thinking, if I don't have enough IO to do 4, because I would basically need 4 like analog RGB LEDs in order to do this color scheme thing, right? You wouldn't get the monochrome gradations at all, but at least you would get the 4 main colors for color schemes that had them. So yeah, 4 would be the minimum. So I'd need 12 PWMs. Like, if I run out, maybe the best thing to do is to just make like a little expander board based upon another Pico, right? Or another RP2040, and do it that way, because that way it's a little more generic and maybe a little more future proof and supply chain proof. Okay, so that's the encoders. And then we need some buttons. These encoders actually have buttons in them. So if you push the shaft down, it's just a momentary button. It has like pretty good tactile feel, but I'm not sure if I want the same thing to do that. I don't know if I want the knobs to also be my buttons in this case. I don't know. It's a little nicer, I think, to have a separate button, and buttons aren't all that expensive. So, and you can have more variety of like nice clicky tactile feel, which I think is very important. I'm very particular about how buttons and switches and things like that feel. I think it is a key part of user experience to be able to have the right kind of tactile feel for the task at hand, Let's see. And then, so I also have a ring LED hooked up right now, and just kind of got that up and running with some of the RPi example code last night. And so, yeah, so let's talk about the code and the software environment a little bit. And I will go back to sharing, I think. Okay. So I'm sorry, I think this is going to be a little bit small, but I'm hoping it's big enough. I did actually make the font bigger on my computer just for this. So what we're seeing right now is this is VSCode that I'm using, and it's with the Platformio extension. So VSCode gets you all of these little toolbars here, and you have your file explorer. So these are all of the files in my project here. search bar. It has some source control built in, so you can actually like push and pull from Git right there. I tend to use source tree running separately just because I like to do that separate. And I know some of you love the command line. That's great. I love me my GUIs. There is a debugger here, and I can talk about that a little bit later. And then this manages all of your extensions that you've installed into Platformio, and then, or into VSCode, and then Platformio is one of these extensions. So Platformio, so this is the menu for Platformio. What it allows you to do is easily compile and upload your code to your processor of choice. VS Code by itself is mostly like a really cool code editor that then needs other plugins and things in order to be fully capable of like debugging and loading code. Platformio makes it pretty easy. It's like a single click to build and then a single click to upload. So not too different from the Arduino, IDE in that respect. It also has a serial monitor built in. You can also choose to upload and immediately monitor, which is nice because that way you don't miss starting messages that are like very first spit out of your serial port, like maybe during setup or something like that. And then there's your clean and clean all, which is to start fresh and recompile everything. So yeah, that is Platformio. This sort of structure is kind of Platformio specific. I'm not following the full Platformio guidelines right now. They, for some reason, like to separate out .h files and .c files. So they like to put .h files in the include, and I haven't quite gotten there yet. I'll do that eventually, probably, just to sort of be compliant, but I'm kind of used to having them all in the same place, and I just didn't want to. A lot of times when I'm developing code, I'm like going back and forth between the header and the C file because you're adding functions, you're doing new function prototypes, and I just like having them. I like to not have to click a bunch in order to get between the two, right? So that's what that all is. I have imported some console code from the class. Elecia kind of gave us a start for a command line interface for our embedded projects that then we could add functions to and have do different things. So I grabbed that existing code and dumped it in here so that I can actually run some pieces of my code from the command line. I haven't really implemented that yet, but it's there, and that will eventually be the serial data interface where you can say, give me all your LED data, and it'll spit out RGB values for all of the LEDs. I'm just seeing you, David. I feel called out right now. Command line lovers. Yep. Yep. So that's what the console IO is, and data right now is just a dummy data that the console IO is using for testing. Encoders are my encoder drivers that I'm still working on, but they basically do very basic encoder reading and tell me direction and like kind of number of clicks, number of detent spaces, so that I can start telling the code like how much do I want to adjust the red up and down, or how much do I want to move that angle of the split complementaries away from each other. And then main, of course, is my main program. And pinout, I just put in a separate header. This is changing a lot with the dev board, but this is just, the pinout of the Raspberry Pi, what things are on what pins. Utils is something that I made, and I basically just made a little file for helpful general functions, like doing a heartbeat blink with the onboard LED, just so I know my program is alive. It's actually not doing that right now. something that does the time in milliseconds instead of microseconds, which is sort of the Pico default. But it's kind of annoying. Like a lot of times you want to enter numbers, you want to define numbers, pauses, waits, whatever, in terms of milliseconds. If you do it in I could do it in microseconds, but that adds a lot of zeros and then makes it harder to see at a glance, like what it is. Like, oh, is that 1 second? Is that 10 seconds? Is that 100 milliseconds? I don't know. So I'm just used to seeing things in milliseconds, and so I made a time function that does that that does everything in milliseconds. And then, yeah, that's about it right now. There's a, heartbeat for the LED pin, and then heartbeat initialize. So it just sets that LED pin to out. And you can kind of see right here. Let me talk about the platform that I'm using with Platformio a little bit, because it is probably not what you might think. So I'm going to go, so this is Platformio home. So I'll go, go to open. So this is sort of the, home page there. And we'll go into platforms. So I have 2 platforms installed here. Raspberry Pi RP2040 is the Raspberry Pi platform. I don't exactly know if it's like Platformio that's in charge of it or Raspberry Pi who is in charge of it, but it is as close to an official Raspberry Pi port to Platformio. However, you might notice right here, this is a list of frameworks supported, and frameworks mean sort of underlying software layers. So any chip has a whole bunch of setup files and generally a little bit of software that is provided by the vendor of that chip that helps you quickly get the different pieces of it up and running. So Raspberry Pi has given us this entire SDK, software development kit, and they've done a pretty good job of documenting it. It is a very, very long PDF, which you do not read from start to finish. You kind of read in chunks as you need them. And it tells you, oh no, see you later, Bob. Catch you next time too. The Raspberry Pi SDK document goes through all of the software that they've already written, and it gives you a very terse overview of what the different functions do. It's my experience that you still need example code to help you know what things you have to set up in what order. And actually, the data sheet is extremely good at telling you that kind of stuff. I know that a lot of software people tend to not read the normal data sheet as a software development tool. They think of it mostly as oh, this just describes the hardware and the board, what you need on the board and stuff like that. But it goes through all the registers and it describes what you have to do to set up each component of your chip and, start making the IO do things and how to set a pin up as an input or an output and things like that. So if you're ever struggling with that kind of setup, definitely looking at the data sheet is good. So yes, but the SDK is sort of one layer on top of that, which gives you sort of human readable-ish functions that do things that you might be able to sort of intuit. But what's even better is the Raspberry Pi examples repo on GitHub. So they've already done just a ton of examples. There's your basic hello world with both serial data and USB. And let's see, there should be a blink. There's your blinky version of the hello world, right? Hello world actually spits hello world out of a serial port or out of USB. Blink, is your hardware hello world, which is blinking an LED. Yeah, Terse is right. Yeah, David, it's I feel like so much improvement could be made in that area, but of course it's the last thing that gets done, right? Is the documentation. And yeah, that's a thing. That is definitely a thing. So, but the examples are better, but they still don't necessarily tell you why they're doing what they're doing, you know? So there's still just a lot of digging through code that you have to do, and a lot of reading of data sheets and SDK pieces that you have to do in order to piece things together. So yeah, the cool thing was, oh, this is all of Raspberry Pi. Hang on, let me go back to the Pico stuff. So yeah, Pico examples, whole bunch of stuff like ADC examples, Hello World, GPIO. So I went down to the PIO here. The PIO is an interesting thing that is like in maker microcontroller land is relatively unique. They have this programmable IO state machine. And it's like, this is a lot of words that could mean like a lot of things that are kind of generic. But what it means is that you can write assembly-like code for the Raspberry Pi Pico, and you can do a lot of things concurrently with one clock cycle. And that's super cool. So you can, instead of like, you know, sort of the normal thing with microprocessors, right? You say like, okay, set this pin high, set this pin low. And maybe if you're, you know, super tricky, you'll like kind of write all of them at once to one port. It's like a little bit like that, but it can also do things like grab other data from other buffers and shift data out and do all of that in one clock cycle, instead of being each individual instruction that might take like a few cycles each. So it's really neat. It means that you can write code that doesn't necessarily block other things that your microcontroller is doing, which is really important when you're talking about LEDs and you're talking about LED animations. Because I'm sure if any of you have played with like the NeoPixel library, most of those animations are blocking. So, you know, they'll have a piece of code like do this, do that, do this, do that, and then repeat, and that's the whole animation. And until that animation has completed once, you know, you can't really do anything else with your code. Like, you can have button interrupts, but you can't handle them to make your code do anything else if you've written it sequentially like that. So PIO would actually let you like send things to the PIO and run some LED animations while your main code is like off pulling pins and doing other things. So it's pretty cool and pretty powerful. But man, aren't I glad that they, did some example code with this to begin with. So these are all the different things you can do with this PIO interface, which can be hooked up to pretty much any output pin. And look at that. They have an example for our good old WS2812 LEDs. And so what I'm running right now on this, and I'll plug it in a second, and I'll show you why it's not plugged in right now. I just went with the most basic example, which is this WS2812C. And yeah, like, let's see. So these are the instructions that like make the patterns. And then, but it's crazy. Like, let's see if I can find it. So this is, yeah. So this is kind of crazy. Like, this is basically the code that drives that programmable LED interface that creates like the very specifically timed pulse train that you need to for this one-line communication for addressable LEDs. And if you want to learn more about that, I did this really great video on it in conjunction with Make, which is only like 10 minutes long. So you should totally watch it, because we actually like look at those signals with the logic analyzer and look at the ones and look at the zeros. And yeah, it's kind of cool. But yeah, basically like 4 lines of code create that train, which is like kind of cool. So anyway, so they have this example. what I did was I like broke it up into, go to my file explorer here. I broke it up into like a .c and a .h file so that my own main.c could you know, use them. And I kept their patterns. Like these are a little bit blocking, but they're just examples, so that's okay. And you, so yeah. They had in their main loop, they have this part that, let's see, there we go. So they had in the setup part of their main loop. Now, if you're used to Arduino code, things are called things that are a little bit different. In Arduino, your while one here is your loop, and everything that comes before that in your main function is setup. So that's it. That's the whole difference. So this is all of our setup. You'll see that that their code had you print WS2812 smoke test. I was like, oh, that's interesting. And then when I plugged it in, I understood why they called it smoke test, because it is at maximum freaking brightness. All of these LEDs are super bright, and like, yeah, we're gonna make that big just so that you can have like the full effect of the super freaking bright LEDs. Plug it in again. So yeah, it like kind of really is that bright. I had it running for maybe 5 minutes on my desk last night, and like I went over to touch them and I was like, oh, these puppies are warm. So, you know, thing number one to do will definitely be to implement some brightness control on this. But yeah, so it sort of randomly goes through different patterns. It is actually doing a white pattern right now. It's not that blown out, but oh, there we go. You can see some colors there. All right, cool. Yeah. And so of course, when I undo the data in pin, it just basically, the LEDs latch at their previous input. So in order to like completely power it down, I also pulled the power pin there. So yeah, so that is LEDs. I did some encoder test code first, and then put the LED code on top of that. So right now they're both kind of fighting with each other, and they're not, you know, you can see, let's see, let me go back to a better view of the screen share. Hello, losing my mouse. All right, so we'll go back to there. So right now, so you can see that I have some serial data output. The LED code is outputting the pattern that it's doing and whether it's going forward or backwards in the pattern. There's sort of like this direction toggle. And then my encoder code is telling you what my right, middle, and left encoders are set to. And so right now it's updating very, very slow because those LED patterns are blocking. But eventually it'll update. So I'm just gonna like move my encoders a little bit, and the next time it updates, you'll be able to see some, oh, we're way, God, yeah, remind me later, geez, get out of here. Okay, we'll be able to see, there you go. So now you can see that like I actually moved my encoders, and you know, I moved my right one counterclockwise, so it's negative. You know, middle I did left and right, and then left I did all one way. All right, got some questions. Let's see. Oh, what hardware wise is running the PIO? It's like a separate hardware module. Yeah, it's so the Raspberry Pi Pico, like the RP2040, is freaking, it's kind of crazy cool. Usually with processors, especially ones that are like M0s that are relatively small, they're like the sort of smallest of the 32-bit processors, right? Maybe not the smallest, but like smallest of the ARM structured ones. So usually you're like, okay, I have like 4 PWMs and they can go to these specific pins. I have like 8 ADC channels, analog to digital converters, and they can only go to these other pins. And then you have like a UART, which is your serial transmit and receive. They can only go to these 2 pins, and so on and so forth. You have like specific pin definitions for specific peripherals. Raspberry Pi, it's like basically completely mappable, like anything goes. And it's like pretty much actually truly mappable, not one of these things that like is almost completely mappable, and then you end up always designing around these weird corner cases where it's like, oh yeah, well, you have up to 3 UARTs available, but only 2 if you use SPI, like that kind of a thing. It's like, no, you really have all of these peripherals available. Your main limiter is pins. You only have like, I forget, 30 or 32. I think there are 32 pins, but only 30 are out on the Pico, or maybe it's the other way around. There are 30 and only 28 out on the Pico. But whatever, you have about 30 pins, and like your only limit is those pins. Essentially, you can put PWMs out on, I think, almost all of them. Like, well, you can map them to any one of them, but you have like tons of different modules. I want to see. Let me see if I can. Let's look at the datasheet actually. So we have Raspberry Pi documentation. They have all this stuff linked on their website. Let's see. This is SDK setup, getting started. I want the RP2040 device datasheet. So this is also a monster of a document, of course, like all data sheets are, with a big old index telling you all the good stuff that you can read about. Ooh, that was the pin diagram. There we go. So okay, so you're limited on clock GPIO. Oh man, you can only have like 6 pins for that. But like, as you can see, everything else, it's kind of amazing. So you have 8 PWMs available, and you can map those 8 PWMs. Like PWM 0 can go to GPIO 0 or 1, or it can go to 16 or 17. You can almost map like every single thing to every single thing. You have 2 different I2C buses, and you can map those to practically like every pin combination. You have 2 UARTs, and you can map those to pretty much every pin combination. Same goes for SPI. So like, you can have all your SPI peripherals at once, and they're not going to conflict with like your PWM peripheral unless you run out of pins. So anyway, I think that's super cool. That is not, microcontrollers are not usually that flexible. So yeah, the PIO is what we've been talking about for like that little super efficient assembly code that lets you do a lot of things at once. And there are 2 PIO blocks. There's like 0 and there's 1. And I think each of those have like 8 different like of these state machines so that you can do different functions with them. So actually, if you're like, shit, I really need a 3rd UART, you can actually make a UART out of the PIO modules. I don't know how many of the little state machine things it takes to do that, but they have example code for it. You can figure that out. It's pretty freaking cool. And yeah, it has native USB so that you can spit out, the USB pins, those are dedicated. Those don't count towards your GPIO. They're like separate pins. They kind of have to be, because they have to be 5 volt tolerant, all that kind of stuff. But these are your extra pins that control USB overcurrent detection, voltage detection on like the 5 volts, enable, disable, that kind of stuff. Yeah. Another interesting thing about the Raspberry Pi Pico, or about the RP2040 and the Pico, that is kind of different from other processors. Let's see, where am I? So I'm going to look at this platformio.ini. This is like extra build flags, extra stuff that's specific to Platformio. Oh, actually, before I go on to that, let me finish my thought here which has taken me a while. I got sidetracked, sorry. Raspberry Pi Pico only has the Arduino platform. So this is like sort of the official Raspberry Pi integration into Platformio. You can kind of only use it with the Arduino setup and the Arduino code base, which does use that Raspberry Pi SDK, but also has to be flexible for a whole bunch of other microcontrollers and things like that. So their code tends to be more complicated and slower because it has to do like all of this checking and mapping so that it can handle like an RP2040 as well as like an Atmega 328P, right? And like the same functions have to be able to be used on both devices. And so, you know, that makes things a little bit suboptimal. I am confused as to why the only option is Arduino and why they don't have like, hey, just our SDK, which people are sort of calling bare metal. So enter Wizio, a third-party platform. You do this through the advanced installation and put in the address of the GitHub repo, and then it installs the Wizio platform, and that's what I've been using. That allows you to select just the bare metal Raspberry Pi Pico SDK and not have to deal with Arduino functions or the Arduino like setup and loop structure, which is kind of cool. They've also done some cool things. Oh, interesting. So Tom has given me some encoder advice. I'll come back to that. That's interesting. I want to ask you some questions about that. So the other thing, there's some things that are sort of specific to the Raspberry Pi Pico. It uses like a UF2 system to load code onto it. So it mounts to your computer like it's a USB device, and you drag a file over to it, kind of like you would for, you know, CircuitPython stuff, right? If in a development environment where you're developing a lot of code and, you know, you want to quick, you know, go through these test cycles. Oh, I changed this one thing. Let's see how it is. It's kind of like a lot of clicking and stuff. It would suck to have to like build it, then drag the file onto it, and then wait and, you know, go through this dance. You also have to put the Raspberry Pi into boot mode in order to like load new code on it. And that's done via, you know, show you that real quick, via this button on the Raspberry Pi. So there's like a button on it right there. So that puts it in boot mode, but you have to power it in the boot mode. So, you know, there's this Pico shuffle dance where you have to unplug the USB, push the button, plug it back in. Now it's in boot mode. Now you can like load a new UF2 on it. And I was just like, oh God, for every code change I want to do I have to like do this freaking hokey pokey thing? Well, one thing you can do is you can hook up essentially a reset button. There's this run pin, and you can hook up a button to it and ground that, and that allows you to at least reset your microcontroller so that then you can like, you know, press the boot, reset, then unpress boot, and then it'll be in like happy code accepting mode. However, whoever developed the Wizio platform has kind of taken care of all that for you. There are some USB commands that will do all of that stuff for you, and they have implemented those. So it is a one-click process. You don't have to do the button dance. All you have to do is click build, and then click upload. And it's sort of like a standard processor, again, in that respect. So that's super cool. The second Pico here, this is my Pico that's running the code. This Pico here is being used as a debugger. So it has a special UF2 that Raspberry Pi, you know, released for it that turns it into a Pico probe. And so you can see that it is hooked up to my SWD pins here. These are normal debug port pins on my target Pico, and so then it is plugged into my computer as well. I'll talk about that in a second. And it basically allows you to stop code execution on this one and go through it line by line and look at registers and see what your variables are set to and do kind of, your normal high power debugging that way. And that is all working with Wizio and Platformio. That's super cool. The one change that I had to make from how to do this all is documented in the Getting Started with the Raspberry Pi Pico, which is a really good reference. But they have it hooked up so that you only have one USB connection to your computer, and that's through the debug. And they have the Pico probe also handling loading code onto this in like a normal way, so that you can basically just have one USB connection. You can reflash, your Pico here through that, as well as debug. That part of it does not work with the Wizio platform. I don't exactly know why. I think there's just extra capabilities that they have not implemented that allow you to do that programming through the Pico probe. So I basically have their power completely separated in the Raspberry Pi Getting Started with Raspberry Pi datasheet. They have you powering your target Pico off of the USB output from your Pico probe. But since I have the two of mine connected to two separate USB ports on my computer, bad things kind of happen if you have those two 5 volts, going together. So that's the make them fight part. Don't want to do that. And so, yeah, so I have them individually powered. The power is isolated for those two, although their grounds are hooked together because they needed that to be able to work. But yeah, the 5 volts is isolated between the two. But yeah, it's all up and running, and it's really nice that I don't have to do the button shuffle dance in order to reprogram this guy, and I can still debug with this guy totally fine. So that, yeah, it's not a big deal to just stick another USB thing into my computer. So the other thing about the USB is that, okay, so back to Platformio, back to our INI file. So this takes care of some of the USB and UART settings, and also sets you up for like the framework, which is bare metal, debug tool. We're using a Pico probe. This upload protocol Pico probe doesn't really work. That's basically what I just got done telling you all about. Monitor port and monitor speed are for your serial data over USB. And that's the port that's hooked up to my actual target. Now, these build flags. So the Pico has this really cool feature in which you do not have to actually change your code in order to change where your UART data is going. So you can choose to have your serial data coming out of the actual hardware UART pins, which are these ones, pins 0 and 1. Or you can have it choose to spit it out of USB. Or you can choose to have it do both, which is what I'm doing with the code, which is what I will share with you because I've just been talking about that. Sorry. So yeah, forgot I wasn't screen sharing here. So yes, framework is here. Bare metal, debug tool, Pico probe, upload protocol, that doesn't work. But these build flags, yeah, basically with two build flags, you can tell it, okay, I want serial data out of USB. That's what this one says. And this one says, oh, I also want serial data out of the actual UART. And you don't have to change your base code at all in order to do that. And that is kind of magical and kind of very neat and interesting and super useful for development, I think. So yeah, I don't have to have like a third serial port, right? That's a UART to or a third USB, which is like a UART to USB adapter, because everything just gets automatically spit out of the main USB port. Yeah, and I have some notes here on how the Pico probe is set up, what's working, what's not. Yeah, cool. I think like that's about it for right now. I am really stoked, even though this code like doesn't really do anything and only sort of works. Like part of getting started with like a new processor and writing code that's new to you is just getting something to work on the thing that you've just plugged in. And so when I see colors on the LEDs, it's like, yes, okay, now we can work on solving, the problems of like, like brightness and things like that. Blocking is actually like animate. I'm not going to be writing animations for the palette, right? They're just static colors that change according to knob changes. So the fact that the animations are like blocking other code, like that doesn't even matter to me for this application. But it does matter like on the death board, because when we on our sand board that we have like backlit with LEDs, we have a button that lets you cycle through different color patterns, but you have to wait for the color pattern to be done before, it'll actually change it, which is a little bit sad. But that's only using I think it's an Adafruit Metro Mini, so it's a 328p. So, we don't have the cool PIO non-blocking options. We'll have to take care of it in different ways, in different software ways on that. But yeah, I'm really stoked that it's just reading encoders. At least it is sending stuff to LEDs, and now I can work on like encapsulating them more and having it, do things in sequence, start to build up the state machine. And yeah. One thing I'm going to do, so encoders. So Tom says, without seeing your schematic, can't say for sure, but you might cheat death and diode or your rotary encoder switches into one single interrupt pin. I could, but like, I can interrupt on any of those pins. Because the Raspberry Pi Pico is super cool, right? So yeah, I can just, it does have only a single interrupt for all of the IO pins. So you have to then like check to see which IO pin actually fired your interrupt. But like that's super easy, yeah. So I can actually have like individual interrupts for both the A and the B phase for all three encoders, and for like all three buttons if I wanted to hook up, the three encoder buttons as well. But the thing that's not working super well about encoders right now is that I was doing like a very super simple debounce when I just was using one of them. And since those are switches inside of there, creating that square wave, they do bounce. And so right now it's not doing a very good like counting estimate because it's sort of bouncing all over the place. So rather than like try to set up like 6 different timers for debouncing 6 different freaking buttons plus whatever other just buttons I use, I'm just like, screw it. I'm gonna just sprinkle some RC filters on this thing and take care of it in hardware, and make my signals clean to begin with, because I don't feel like debouncing all of that stuff in software. And besides, if it's a kit, you want more stuff to solder, right? Hell yeah. I heard that hell yeah over the internet. Okay, cool. Yeah. So I don't know. I think that's pretty much all I got right now. And I want to catch the homework session. So, but tell me, David, if you are still around, I saw something that might be relevant to your interests. So we're not using Arduino framework for this class because sort of the point of the class is to use vendor provided SDKs and sort of standard C, a standard C like function, main loop setup and stuff like that. But I am not personally against using the Arduino framework at all, because it makes it very accessible to a lot of people, right? And we like that. So when I was installing it, where am I? PIO home. When I was installing that, where? Maybe boards? No. I don't know if it'll show it to me now that I've installed it. Here we go. Check out the supported boards for the Raspberry Pi RP2040 framework. It not only supports the Pico, but also the Nano RP2040 Connect. Ooh, ooh, ooh. Yeah, I thought that you might like that. So we're working on. I don't know. I'm not ready to spill the beans about it yet, but David's working on like a cool little project that might have some potential textile electronics cool crossover things that we might be able to like eventually potentially make into like kits and stuff. So anyway, but the RP2040 Connect is a board that he was thinking about using as a little development board for that. So yeah, so you could do that with Platformio and the standard Raspberry Pi RP2040 with the using the Arduino framework if you wanted to. Yeah. Yeah. Shh. Secret. Meow meow secret mission meow. Tom will get that. It's shaking its head at you as we speak. Yes. This is so good. Meow meow secret mission meow. In case you don't get that, you should all look up Predator in 10 seconds. It was a good early internet flash animation thing. Meow meow secret mission meow. Yeah. I think that's going to be our code name for the project now. I think that's it. I mean, it is incredibly fitting. Flash. All right. I think that's about it. If anybody has any other questions, like about what the fuck I've been talking about, either the Palette final project or Platformio or the RP2040 and what you can do with it and why it's super cool, like feel free to write in the comments. I will pause and take a drink of some electrolytes. It's just electrolytes. It's not beer right now. That's kind of sad. I got to go to homework session though. I can have beer after homework, right? All right. Well, I shall take that as a sign that I certainly confused everyone. And that there are no questions because the head is just going. Cool. Well, thank you guys for joining. And yes, I think next week we also don't have a guest, and I could also probably use a little bit of extra homework time. So I might just like update you on this and talk about maybe we might have some other Alpenglow projects that we've been doing around the house that are ready for sharing. So yeah, I might share some of those with you too. Cool. Awesome. We will see you all next Wednesday. And in broadcast, playing out. Ooh, yeah.